Bom dia a todos, sejam bem-vindos ao webinário da PharmaFluidics. Meu nome é Luiz Bravo, sou da Analítica. Nós estamos iniciando um trabalho com a PharmaFluidics da Bélgica. Estamos trazendo hoje o Dr. Robert Van Lien para fazer uma apresentação dessa tecnologia. Ele tem larga experiência em nano-HPLC, iniciou os trabalhos com a empresa LCMS. Essa empresa foi uma das pioneiras em nano-HPLC. Após alguns anos, ela foi adquirida pela Dionex, e em seguida, mais alguns anos, a Thermo adquiriu a Dionex. Então, hoje, muito dos nano-HPLC existentes ainda possuem tecnologias que vieram lá originalmente da LCMS. Robert tem uma boa experiência com proteômica, com ciências ômicas, trabalhando com proteômica em várias escalas, desde pesquisa, clínica, proteínas intactas, com anticorpos monoclonais, e ele vai trazer um pouco dessa experiência para a gente, mostrando essa tecnologia, que é uma tecnologia bastante revolucionária. Eu costumo dizer que é onde a fase estacionária realmente fica estacionada, e agregando uma série de benefícios. Então, o objetivo do seminário é levar esse conhecimento para vocês dessa nova tecnologia. Vou passar a palavra para o Robert para ele iniciar. Robert, go ahead. Good presentation.
Thank you very much, Luis. Welcome everybody, also from my side, for this joint webinar that we do on the microPAC. I think I understood correctly. So my name is Robert Van Lien, and what I try to do is help support our the people we work with in sales, but also as users, to move forward with the separations in an omics or omics-related research environment. And hopefully, in the next 45 minutes, I can show you what we can do with this micropillar array column, or microPAC, as we call it in short, and how we can improve not only the analysis, but also help improve the throughput of the samples that you need to do. So if I look at the story of this webinar, is enjoy the beauty of pillars. I've just taken a beautiful image from a nature site in Russia, but the beauty of the pillars could be translated to something like this. And we are going to use pillar technology to create mass spectra like these, to create protein IDs, hopefully in the range of the numbers that you see beneath here. And the pillars that I want to talk about are located inside our column technology. So as you can see here, schematically, we have an input of our sample onto the column, and we have lanes connected with each other where these pillars are brought. And because we have this going back and forth within the lanes, we actually can achieve, on a very small format, a column that has a length of 200 centimeters for separation. So what I want to do is first give you a brief introduction of the company PharmaFluidics, the product, the microPAC, and also the connectivity to mass spectrometry. We aim especially at the omics people, and even more specifically at proteomics people, which means that the detector of choice very, very often is the mass spec. From there, I'd like to dive into more routine and comprehensive workflows or classic nano LCMS applications using the two types of columns we have for that. Then I'd like to dive in a relatively quickly upcoming field, which is the single cell proteomics, where we have extremely limited sample amounts, and we need to do still that in-depth characterization of the proteins available. On the other hand, we have something that we call clinical proteomics, where we are more interested in speed because we have large sample amounts that need to be analyzed. After that, I'd like to take it into other smaller sample omics like lipidomics and metabolomics, and also in some high sensitive LCMS methods like the characterization of biopharmaceutical proteins and enzymes. And I'd like to close that with a short summary, and then of course I'll be open to any question you may have. If you're afraid to forget the question you had in mind, just type it into the chat box, and we'll discuss the question after the presentation as well. So introducing the microPAC column starts basically with who is the company PharmaFluidics. So we are a spin-off of the Free University of Brussels, and we're located in what we call the Flanders Life Science Valley, which is very close to the city of Ghent. And as you can see, we've got some of the equipment in our own facilities that you probably recognize from your own labs. So we do have nanoLCs, we do have some mass spectrometry, and we are currently also reinstalling our clean room facilities to be able to expand further and further into this field of technology. Our key expertise lies in the design and the manufacturing and the surface treatments of microchips that we use for the separations in nano and capillary LC. And with that technology, we think we have a key to extra high resolution chromatography, so we can identify more molecules with higher sensitivity in small and especially in complex and very complex biological samples. We can do that with ultra high reproducibility. The key of the technology lies in the fact that we can make these type of separation channels enormously accurate all the time, creating extra reproducibility for the results that you need. And as a result of the manufacturing process and the way the pillars are established, we can create really, really good robustness of the column, which often is considered one of the problems in nano LCMS. Now, who are the people behind the company? And to limit it off, I've just taken some of our scientific advisors. Of course, the first one here that I have to mention is Professor Gert de Smet, a well-experienced chromatographer, just like Professor Pat Sandra. Professor de Smet is actually one of the co-founders of the company and is the head of the group that started the developments on the pillar array columns. Professor Pat Sandra also is a very well-renowned chromatographer, and we work quite a lot in combination with his company, the RIC, or Research Institute for Chromatography, and you will find his name back in some slides during this presentation. Another of our advisors is Jean-Pierre Chevet. Jean-Pierre is actually the founder of LC Packings. That is more or less one of the original nano LC companies that were on the market back in the early 90s. And is also the company where I started working with nano LC in 1995. Nowadays, he is mainly the CEO of Antec Scientific, but again, also part of our advisory board, just as Professor Matthias Mann, probably the best known proteomics researcher nowadays from the Max Planck Institute in Munich. He also has a group in Copenhagen, and he also, in his group, is using the microPAC technology for highly complex samples, and you'll see the example later in the presentation. Now, considering where we come from in the development of the micropillar array column, just imagine that many, many years ago, we used to work with columns packed with very irregular shaped particles of not always clearly sizes of the particles. And over the years, a lot of chromatography companies have worked really hard on improving that backbone for the separation. They came up with 10 micron particles. When I joined, we were standard-wise working with 5 micron particles. And from there, we moved every time to smaller and smaller particles. Probably the biggest upset was in 2004 when Waters introduced the UPLC with the sub 2 micron or 1.7 micron particles. And after that, it's slowed down a little bit in the development. We certainly see the solid core particles, so it's a slightly larger particle, but with a very small porous layer around the particle to mimic the sub 2 micron particles. Because one of the things that you see with these smaller and smaller particles is that you get higher and higher back pressures that the pump needs to deliver to get the sample separated through the column into the detector. Next to that, the challenge in size distribution of the particles has not really disappeared. So if you open up a column and you carefully measure every individual particle inside the column, you will see a size distribution that is not perfect. Now, in that different sizes of the particles, that might lead to a packed pad that's not as stably and forcefully packed as you'd wish it to be, which might over time create voids and might hinder in both the lifetime of the column and the reproducibility of the column. So taking all these challenges together, that's where Professor De Smet started at the university, and he worked on an idea that had been around for some time, and that's, can we create a new type of backbone, the pillar backbone? And as you can see here, in the little picture of the pillars are created in a lithographic technology, which means we have a silicon wafer, we put a mask on there, we put the correct chemistry on there, and we etch our way down and create the separation channel. So the pillars are part of the original wafer, which gives us quite some extra strength. Now, because of that technology that we heavily use in our daily tools like mobile phones, smart watches, and things like that, it is a highly reproducible technology to create such a pillar backbone. Because it is also a very accurate way of creating the pillars, we can play around with the positioning and the ordering of the pillars. So what we have done is not only created a perfect array of pillars, but we've positioned them in such a way that we reduce the back pressures required to go over the column. And all that together helps us improve the resolution that we can achieve, the reproducibility that we can achieve, not only from injection to injection, but actually from column to column as well, and also improve the robustness. Now, going back to my early days, many years ago on nanocolumns, I've put in here an image of an old paper that we did back in 1996, where, as you can see, the instrumental setup of the nanoLC looks a little bit different from how you would use nanoLC nowadays. So we used to use two pumps providing their own solvent, and they were mixed and then split it down to the correct flow rate using this little splitter box. We had an injector and then the column. And the column looked quite a lot similar to the picture you see on the bottom here. So we had a fused silica packed bed column. And with that, you got a PEEK sleeve, a nut and a ferrule, and you had to put these together, put that carefully in a valve and tighten it yourself. Risking also the fact that you could over tighten it, break the front part of the column, and you would have to replace the column with a new column. Now, again, what has taken a lot of effort is the development of these connectors like the nanoViper connectors that we introduced at Dionex and currently are part of Thermo, and like Waters with the ZenFits. And also, of course, the more integrated forms of LCMS where the emitter and the column are connected from the factory together, like with the Easy Spray and the ion key. What we like to do is take these two still a little bit apart, because in this final setup, if your emitter goes down, you can't replace the emitter, so you'd have to throw away the emitter and the column. And as you probably have seen in your own lab, in your own experience, the emitter is typically more fragile than the column actually itself. So what we have done is created this pillar array, as you see here, and as you also see the waver that we use. So we have a small silicon waver, and from there we can create 2 meter long columns, 50 centimeter long columns, and we can actually create trap columns as well. All these pillars are positioned in lanes, in an array that helps us move down until you actually see the pillars shaped like this, and on the middle image you can actually see the porous layer that we use for the separation, and here the zoom in of the porous layer. Now to connect, we have standard 1/32 inch connections, but we also can use Viper tubing or our own finger tight connectors to make the connection really easy to a nanoLC system with 1/16 inch connections. And on the back end, we have simplified the connections to mass spectrometry as well. Here you see the difference between the traditionally packed bed column on the left and the highly ordered separation bed from the pillars on the right. And the result of that is that without those voids that will occur in your packed bed, we actually can narrow down the peak shapes that we obtain. And if we can narrow down the peak shapes that we can obtain, we can actually try to put more peaks in the same gradient window. That's what we call the peak capacity. Now, if we can have a higher peak capacity in the same separation window, we can actually start to separate out more compounds in our sample. And if we can have less co-eluting compounds per sample, the mass spec can actually spend more time per compound in that same gradient separation window, giving us a better score, a better identification of the proteins we're trying to either identify or quantify. So it's quite important that that high peak capacity is available for the separation. Now, this is just an example which I hope you'll not be very interested in to reproduce, but it gives you an idea of the capabilities of the microPAC column. So this is a paper which is done by the group of Professor De Smet. Now, I mentioned our column working, the microPAC working at reduced back pressures. actually, this is a 4 times 2 meter column coupled together. So it's an 8 meter long separation path, and we still work below 300 bars. But on that separation path, using a 2,500 minute gradient, we can actually simply achieve a peak capacity of just under 2,000 peaks. Now, just imagine you have an enormously complex sample available with thousands and thousands of proteins that you cryptically digest, so you'll end up with hundreds of thousands of peptides that need to be separated as good as possible and then be characterized, identified in the mass spec, and then software-wise being built back to the proteins of interest for you. This is a column that can really help you with that. In the combination with the robustness. So this is an experiment we did ourselves, and we took a Hela cell digest. So we did 1,000 injections of the Hela. We alternated each Hela injection with a blank and a cytochrome C injection. So the column itself has seen more than 3,000 injections, out of which 2,000 injections were protein digests. This is the 2 meter long column, and to help us speed up the analysis a little bit, we actually ran the column at 1 microliter per minute, so a little bit higher than you'd normally do in a nanoLC, and we used it in a short gradient, a 30-minute gradient. And as you can see, we have a back pressure from injection 1 to injection 1000 that does not exceed 250 bars. So that means you on the Hela injection. So that means you've had 3,000 injections all running below 250 bars. Now just imagine how nice that will look on things like your pump seals, because they will see the brute force of your high pressure capabilities in the pump. I like the UHPLC and the UPLC systems because they are really, really good in delivering accurate gradients, and they're plumbed through really well without dead volumes. But I don't like to use that high pressures. Now, if you look at the chromatograms to the right, they are very, very similar as well. The one thing that you notice is this bulk coming up a little bit and this peak here with injection 1000. Now, when we started these experiments, we actually made the solvents up to last for all the injections. So you're looking at a 1,000 injection of Hela almost running for 5.5 months on the same eluent bottle with the same non-refreshed eluent. So I call that my green peak. We did use TFA, and that will help not keep the solvent clean. So the reproducibility of that column is extremely good, and despite all that dirt growing in my eluent bottle, we still saw no massive jumps in the back pressure over the column. Now, several users have actually been pushing this idea on the social media, Twitter and LinkedIn. So on your left-hand side is actually a comment from the UK where the person running it actually ran that column at that moment in time for 6 straight months in a row. But I know actually that he's run it now more than a year. And he throws all kinds of proteomic samples on it without any problems, without any loss of performance. Now, on the right-hand side, you actually see a former colleague of mine from the Dionex days who is running a core facility lab in Vienna, in Austria, who has multiple types of mass spectrometers and is running mainly the 200 centimeter long column. And he mentioned that he is now running that for more than 2,000 injections, and it's still working without any performance loss. So that's the type of work I would like you to envision in your own lab. Is you have this column and it will actually perform in a long time. So you don't have to change columns over that often. So you don't have to shut down your LCMS system that much and then start it up again. Just let the column do the work. So if we look at the routine proteomics, I would say the proteomics very often done on a packed bed column that's 15 or 25 centimeter length. That's where I would employ the 50 centimeter microPAC. You can run the same gradients. It's ideal for gradients, say from 30 minutes to 120 minutes. And it will give you that extra resolution just because the column's that much longer. And it will also give you that robustness that we just talked about. So the column will work for a long time at a resolution that's really, really helpful in your LCMS analysis. If you actually have to run much more complex samples, we're going to need a longer separation pathway. And on the packed columns, that's when you would normally move to 50. Sometimes if your pump can do it, 75 centimeter columns, and that's it. And that's where we like to use the 2 meter microPAC. And as I said, back pressure wise, a 50 centimeter 2 micron particle runs around 650 to 700 bar in back pressure. The 2 meter long microPAC column runs around 100 bars. So a significant reduction of back pressures. Because of that separation length, that long channel, it is ideal if you want to really deep dive into your proteome. So ideal for 150 minutes up to, let's say, 600 minutes. So 2.5 hours, all the way up to 10 hours if the sample complexity requires that type of analysis. But of course, that's not the direction everybody's looking for. We also have a growing number of labs that need to run more and more samples and also more targeted, like in clinical proteomics. So that's when we go back to the 50 centimeter channel. So we have this high resolution separation in comparison to the packed columns used for that. But we run that at higher flow rates and typically shorter run times. So I would say if you have this 50, 60, 70 sample per day requirement, you would run that preferably at 5, 10 microliters per minute. And you'd have to run that in 10 to 20 minute cycle times per sample. And that's where we use the microPAC capLC, as we call it. So we can cover high sensitivity, we can cover high throughput and sensitive analysis, and all the bits and pieces in between. Now, if we look at the mass spec connectivity, we can use a multitude of emitters available. So we can set it up with coated tip emitters, we can set it up with stainless steel emitters, where again the emitter robustness typically gains quite a bit, or we can set it in one of the more sensitive modes, which is the glass emitter with a liquid junction. All these types of connectivity to the mass spec will work with the pillar array column. To couple to a mass spec from Thermo Scientific, we're actually quite easy to couple. So we actually have an agreement with Thermo that we can modify the easy spray emitter setup. So we have directly our union on there, so you can directly connect the micropack column to that union and use all the tools from Thermo to then connect the emitter into the source to the MOSPAC. If you use a flex source, we actually have developed what we call the micropack Flex Ion Connect, where all you need to do is push that over the metal rod of the flex source and then connect the emitter and connect the column on one side, connect the grounding cable and the liquid junction, and then you're off and work. And we deliver that with emitters that are 360 micron in outer diameter, so a standard dimension emitter that you can use. But also, if you work with the Bruker mass specs or the Sciex mass specs, we can help you with the connectivity to both of these systems. So both systems will take on the micropack, and I've got a biopharmaceutical example later in the presentation where we've actually used the Bruker timsTOF Pro to look at host cell proteins in a biopharmaceutical environment. Also, we do have really good support people in our group that will help very carefully and very patiently in the correct setup of the connectivity to the mass spec. So if we dive into the application field, talking about capillary flow and nanoflow, the largest field is the proteomics world. So many mass spec proteomics labs adapted years ago to nanoLC and know quite well how to use this technology and what the pitfalls may be when they run their precious samples on the instruments. Now, the first thing we tried to do was benchmark the micropack 50 centimeter column to the standard columns that are available on the market. So in the greenish color here, on the left-hand side, you see the micropack separation on a 50 centimeter long column running at 300 nanoliters per minute, 60-minute gradient with an injection of 500 nanograms of Hela digest. And on the right-hand side, in yellow and gray, you see the exactly identical conditions on two commercially available capad columns that are actually quite heavily in use for this type of work. And the one thing you notice is that the micropack is just a fraction slower in its run times, but don't forget these yellow and gray are 5 centimeter long columns, 15, and the micropack is 50. Running at the same flow rate, it will take just a little bit longer to get that separation out. But the amount of peaks that you can see in the micropack run is significantly higher. And also you can see that the intensity of that base peak chromatogram is a lot higher than you can achieve over the two capad columns. Interestingly enough, because of the low back pressures of the micropack, the 50 centimeter runs at approximately 40 bars, you can also easily speed up that flow rate. So we did speed it up to 1 microliter per minute. And interesting from there is that we see that we can really speed up the separation to even quicker than is possible on the capad columns at 300 nanoliters. The other thing you notice, of course, is the lower intensity that is achieved at the 1 microliter per minute. But don't forget that we injected the same amount of peptide, 500 nanograms, but we used more than 3 times the amount of eluent. So the dilution of these peptides is higher, which negatively influences the sensitivity that you can see in a base peak chromatogram. But if you look at the identifications of the proteins and the peptides, you can see that the nano separation over the microPAC and the capillary separation over the microPAC in a 30, a 60, and a 90-minute gradient remains higher than what you can achieve over either packed bed column. It's even that if you look on the left-hand side, if we look at more the chromatography features, of course the pressures are lower. I mentioned that. So the 50 centimeter runs at approximately 40 bars, and we ran around 125 bars when we used the 1 microliter per minute flow rate. But if you look at the retention times, you can see that the peaks are much narrower, and that whatever the gradient time is, the tightness control is also a lot better than what you get over the packed bed columns. So if you want to run long gradients, we can have a better retention time control. If you need to do label-free experiments, MRM experiments to quantify your proteins, we have much better control over the retention times, which means you can run much more reliant on the retention windows that you measure. If we zoom in on the identification results, even more striking it is when we look at the 30-minute gradient, where we actually find that the 1 microliter per minute flow rate developed or identified quite a bit of proteins and peptides extra. And I think that's one of the reasons why in clinical proteomics, we all move to the low microliter per minute range, because we know we can get that throughput. You saw the shorter run times. And at the same time, we can keep that high level of identification if the sample is not too complex. Now, for the benchmarking of the 200 centimeter column, we looked at the longer packed bed columns, and one of our collaborators used to pack his own 40 centimeter long columns for his proteomics LCMS work. And he used to pack them with the 1.9 micron Dr. Mice material, which is quite an efficient material to run and is quite helpful in packing yourself. Now, if you look at these data, all the run conditions are actually in the paper that you see mentioned here, which is free access through the bioRxiv website. What you can see is we ran both columns for a 210-minute gradient, so 3.5 hours, going into that comprehensive proteomics area. We injected the HECT 293T digest, and we run both columns at 300 nanoliters per minute. Now, as you can see, the packed bed column in orange has a maximum pressure of 450 bars. The microPAC column, 2 meters length, so it's 5 times longer, actually has 75 bars of back pressure. So the pressure differences are massive. But as you can see in both base peak chromatograms, the amount of peaks that are separated in the same gradient is much higher on this microPAC micropillar array chromatogram. What you see in the background is, in the light color, is the pressure. And one thing that you can see clearly is this enormous pressure drop from 450 bars down to almost 250 bars during the gradient in the packed bed column. That's actually more pressure drop than the total pressure used on the microPAC. And like I said before, the one thing you do in your load and eject cycle every time you inject is you go from a tightly high pressure environment on the column to in the load mode to a release of that pressure in the inject mode to a rapidly returning back pressure while you go flick the valve back and you go back to your load mode. And that happens every injection you do. So you push that pack bed really tightly together, you release it in an instant, and you try to bring it back as quickly as possible. And that will create voids in your pack bed, and that will over time influence your reproducibility and the quality of your separation using that particular column. Now, here are the results of that experiment using the 2-meter long column. And in orange, again, on the left-hand side, you have the numbers for the 40 centimeter self-packed column. And in blue on top, you get the numbers that were achieved with the pillar array column. But it's slightly easier when you go to the right-hand side and look at the Venn diagram. Duplicate runs, 3 microgram of the human cell digest injected, and you can see that in the yellowish part, the number of proteins is more than uniquely identified proteins is more than 3 times smaller than we can achieve on that micropack. There is a really good overlay between both column types of the amount of proteins identified. But just by changing over from that 40 centimeter self-packed column to the 2-meter long micropack column, running the same gradient conditions, you can achieve 17% higher identification of protein numbers, which is quite remarkable. And one paper I'd like to show is this one from Toth and Mitulovic, where they used which is a great stepping stone to start with the micropack. Here they, in the first chromatogram here, they describe the method they started with to get the best spread of peptides all through the measuring window. So they had a 7-protein mixture digested, ran that to see if they could spread out the peaks as wide as possible so the MS would have the best time per peak to do mass spectrometry on. From that experiment with the same sample, they started to take a look at the possibilities to create a beta gradient. So they started off with that linear gradient to run, and then they started to look at what happens if instead of a linear gradient, I create a step gradient in the middle. And in the end, they actually found that 2 steps in that gradient are very easy to run, but they could remarkably spread out all these peaks nicely over their separation window. Now, with that in mind, they went back to a Hela digest, and they compared that Hela digest using the 2-meter long micropack with a 50 centimeter long PEPMAP 2-micron particle column. And as you can see here, which is quite remarkable, is that the amount of proteins they found in every run on the micropack is almost 25% higher than the amount of proteins they could find in every run during the PEPMAP separation. And the total number of proteins they could find on the micropack was also significantly higher. And the one thing they checked for us as well was that using the PEPMAP column, 50 centimeter packed bed, the amount of proteins they could identify in a triplicate run was less than the amount of proteins they could identify in a single micropack run. So that's truly the power of the micropack column when the samples start to become really complex, is that extra separation power and that extra peak capacity that will allow the mass spec to spend more time per peak available. Now, moving to the truly comprehensive workflows, we also looked at 2D LC. I remember when we did 2D-LC, starting off with a high amount of sample in the first dimension, running it into an ion exchange column where you use a salt elution and then had to modify the conditions to be able to run it salt-free as possible into a reversed phase column into the mass spec. But nowadays, a lot of people simply use a high pH, low pH method. And one of the methods you could use is the fractionation, like here, 15 high pH fractions made, and then re-injected on the micropack with a 4 microgram loading for 6-hour runs. This was done by the group of Biognosis in Switzerland, and they were able, in every of these 15 fractions, to identify just over 9,120 proteins. And with an amazingly good reproducibility of these identification rates, actually enough for them to say that they've never seen that high result using what they call single analysis. So that's, the column is a perfect fit for highest complexity samples where you want to run 2D-LC. Now the example from Matthias Mann, slightly different. They combined the proteomes of 100 organisms. So these are the 100 organisms. They were mixed, digested, and then run LCMS with the micropack column. And as you can see, it's a little bit small, but as you can see here in the bottom corner, they identified proteins from all 3 organism classes, but they identified more in total than 320,000 proteins. So that is an enormous amount that they were able to identify, helpful through an excellent separation of all these peptides that were in the sample. They actually did compare the micropack to their own self-packed columns. So in a lot of publications from the Matthias Mann group, you will find a 20 centimeter packed bed column, again with this 1.9 micron Dr. Mice material. Now here they specify the spread of the reproducibility times in the sample. And as you can see in the pinkish color, this is the spread of the peptide retention times using the Dr. Mice self-packed 20 centimeter column. So it's striking that the micropack, which is 10 times wider as a separation channel, has a much tighter spread of the retention times of the peptides in the experiments on their equipment. So that means there is much less overlapping of peaks from injection to injection, so you can have more confidence in the actual protein identification you achieve. And again, in this paper, they describe very nicely the conditions they used and the connectivity they used. It's really a nice paper. So here is one of my good friends from cancer research in the United Kingdom. Duncan Smith runs a small core facility lab. He's got 3 mass specs and nanoLCs in the front. And he's adapted to the 50 centimeter micropack. And his main reason for that is that he gets a lot of samples in from his customers that could be relatively simple, like a gel band, but they could also already go into the complexity of small tissue samples. And he says that with the 50 centimeter micropack, he doesn't need to change the column depending on the sample complexity. All he needs to do is just play around on the computer in his method and take the gradient steepness down, lengthen the gradient time to be able to go from the simple samples to the more complex samples. And he can run all that on a single setup without having to change the columns every time, which, as you can see, he considers to be very often a necessary evil. And now he can avoid that evil. That's when you work with 100 nanograms to a couple of micrograms of digested protein. But what happens if you have less sample available? And of course, the most visual application nowadays is what we call single cell analysis. And one of the things you could be looking for in single cells is how does the protein content in a cell behave under certain conditions? If a patient has got a disease, how does that work? You could be looking at stem cells, cancer stem cells, and consider why does chemotherapy not kill off this particular stem cell? Because that is basically the invitation for the cancer to return after treatment. So that type of investigations are becoming more and more popular now with research groups, and maybe even your own group. So what we do for that is we initially started a project where we look at 10 nanogram of protein content in digested form. But as you can see, in comparison to a lot of groups that do single cell type of analysis, we can use a standard nanoLC system. So we run at around 250 nanoliters. We don't need an external flow reduction to be able to use on very small inner diameter columns. We can just use the microPAC. And for this experiment, we actually used the microPAC that I showed you before, the 50 centimeter. We use common solvents, we use 360 micron OD common emitters, and you can see here the gradient profile that we used programming through the Thermo software. From there, all these details are in the paper, again, available through the bioarchive as well. And from there, we again looked at how stable are the peptide retention times when you inject just almost nothing. So 10 nanogram of protein content is the equivalent of approximately 20 cells. If we compare that to the PepMap columns, and this is the 50 centimeter PepMap column packed with 3 micron particles, you can see an enormous difference in the retention time stability with the microPAC compared to the retention time stability of the packed bed column. And that's what we can really use when we look at the identifications. So again, here, identifying the proteins from 10 nanogram injections, and the group we worked with is the group from Karl Meschler in Austria. In a 2-hour gradient, actually managed to identify 2,740 proteins out of the equivalent of 20 cells of peptide content, which is a remarkable number. And if you look at the Venn diagrams, which make the comparison a little bit easier, you can see that the amount of unique proteins that we can identify using this is almost 7 times larger than the ones you can only identify on a packed bed column. So the number of proteins and the number of non-identifiable proteins on a classical packed column is completely blown away. The next step, of course, is diving really into a single cell. So this is a poster we produced last year at the digital ASMS together with Carl's team and the people from Thermo Fisher, looking at 2 to 4 Hela cell samples using a new format microPAC column. So it is a non-porous column, still 50 centimeter long, but the pillars have become a little bit smaller as well. And we run that at 250 nanoliters per minute. And we actually ran that from 10 nanogram sized samples all the way down to 500 picogram samples. And as you can see, we still have very good identification numbers on the proteins. But we tried to take that even a step further, and we actually went down to 0.25 nanograms or 250 picograms. And there you can see that in that setup with a very nice mass spec with FAMES, all bells and whistles are available, using a 1 hour gradient, we can actually identify 1,500 proteins out of 250 picograms of protein content. So that's really the state-of-the-art identification amount that you can achieve using such high-end mass spectrometry, but also the high-end chromatography in combination. And again, at 250 nanoliters per minute. So no downscaling of the flow after the gradient has been formed. And that non-porous column, if you are interested in that column, will actually become available next week. The introduction is going to take next week. But I thought because it's only a week away, I very much like to show you the results on that column. Now, the other end of the spectra is the sample throughput, clinical proteomics. I might have a combination with a hospital and they have 200, 300, 400 patients that get specific drugs, and we are there to monitor the biomarkers on that drugs to see if there is an effect of the drug on the diseased state of the patient. And for that, I would like to run higher flow rates. I work a little bit more targeted, so I don't typically need the highest sensitivity achievable. I will have that high-end mass spec, but I just need to make sure I can run all these samples highly reproducible. So here you have the examples of the start of our experiments, where we used 108-minute gradient time at a flow rate of 2 microliter per minute. So we could basically go into the samples and achieve a nice sample amount of runs that we could do. But like I said, if you have 100 or more patients, you are going to require even further sample throughput. So what we did is half that time, go down to 54-minute gradient time, and that's where we were able to run 24 samples in 24 hours. But still, it's not enough for that high amount of sample groups that you need to do. And most people in clinical proteomics start to look at 60 to 100 samples per day on a single LCMS instrument. So when we moved our gradient times down to 17.5 minutes on an ultimate 3000 system, we can actually hit 65 samples a day without any problems. And as an example, I've plucked here the remarks from Professor Stensballer, who is doing that kind of cohort studies. He not only can run more samples in the normal way, but because of the structure and the features of the microPAC, we know we have a really low carryover, which means that in his experimental phase, he has learned that he can reduce the number of blanks. So he can squeeze in more sample injections in the 24 hours that the lab's working. So he can further push his sample throughput that way. So again, quite a happy and intrigued researcher to be able to do more than he initially thought was possible because of that low carryover of the microPAC. And if it really comes down to it, just speed up the flow rate to 10 microliters per minute, and we ran it at a run time of under 14.5 minutes, a gradient of under 9.5 minutes, and that's when you can really go towards the 100 runs per day. And again, if you do 100 runs per day on a nanocolumn or on a capillary column, robustness becomes an issue, because you cannot every 5 to 10 days change over that column, because every hour you miss, you are going to miss a significant number of runs. And again, that's where the pillar array microPAC is really, really favorable. But outside of proteomics, there are other regions where samples become smaller, because the model organisms we use might become smaller. Metabolomics and lipidomics, we might be looking at the C. elegans or even the zebrafish. And if you want to investigate the brain plasma of a zebrafish, when you take that all out, you end up with approximately 1 microliter of plasma. And you have to get your sample from there and preferably triplicate inject from there. So you have very, very little sample amount available. And again, that's where the microPAC can help. You might have experiments where you are going to need more sensitivity, not necessarily because you have less sample available, but just because you need to dive just a little bit deeper into your sample than you could see on the typical 2 millimeter column. And again, that's where the features of the microPAC will help. So as a application example, what we've done here together with the group of the RIC is we've done some metabolomic profiling using 4 nanoliters of extract. So we have a poplar bark extract, and we injected that on the top chromatogram on the pillar array column, a 2 meter long column, and just 2 commercially available 2 millimeter columns. But the results in the identification that we were able to achieve were stunning. We can have much more sensitivity than you can have on that 2 millimeter column. And the retention time window that we can achieve again becomes smaller than on the PAC bed columns, which means that we have all these chromatographic conditions really well under control, and they do result in better identifications as the end result. Also, when we look at lipidomics, with their complexity, we can, using that extra length column, really push forward the separation, which will help in simplifying the identification afterwards. As you can see, we have a really nice separation of the lipid classes, and then within the lipid classes, if you look to the zoom in, you see a highly complex chromatogram that we were able to create from that sample. And it makes no difference whether you run it in negative or in positive ionization mode. The microPAC will perform in both ionization modes. Also, when we look at biosimilar characterization, Brazil actually is one of the global leaders in biosimilar developments. The new developed biosimilar drug needs to be highly identical to the original drug, but not fully. So yeah, we need to see tiny differences. And one of the ways you could do that is to really, really dive into the peptide structure. And as you see here, on the bottom trace, we've got the original Remicade drug, antibody drug, and we have a potential biosimilar candidate in the top trace. And you can see marked by 1, 2, 3, 4, and 5, the tiny little differences between the 2 peptide maps. But these differences, if they are available and if they are really small enough, you could go for a biosimilar track in development instead of going into a full track. So in that development time of such a therapeutic protein, it is really important. Here, we're looking at a highly glycosylated therapeutic enzyme, which is actually used nowadays in the treatment of patients that have Pompe disease. As you can see, it's got a highly complex glycan structure, even more complex than the average monoclonal antibody drug. But also, as you can see, using a standard approach, we can very, very nicely, in the low microliter per minute range flow rates, separate out and characterize the glycan structures, even down to the level where we know what the predominant glycan structure is, and also in what region in the chromatograms that we obtain they are actually coming from. So we can really dive down into the detail of these glycan structures. And here an example of further down the development path, which is the impurity analysis. When we design a therapeutic protein, it comes from a living environment. We grow that, we let that develop in a living environment. That means that these proteins are being produced in a cell, and all kinds of rubbish is around that cell available. So that typically takes a 3 to 6 stage purification to get that target protein, that target antibody, as clean as possible. But even then, strong binding proteins will be present. And if you have a fully clean antibody that works really well as a drug, these strong binding proteins might interfere with either the working of the drug or even the safety of that protein as a drug. So we need to identify as good as possible the host cell proteins, as we call it. Now, what you see here is the microPAC column used on the left-hand side of all these bars. And on the right-hand side is the comparison to the original protocol that was published by Wang. And that protocol is really interesting because it describes a partial digestion protocol to avoid a complete overload of the peptides from the target antibody, because that protein is by far the most abundant in the sample. So that way, we could reduce that amount of peptide and try to dive into as much as possible the host cell protein peptides. But as you can see, moving from that original protocol into a better PAC bed column and then into an even further and better microPAC column, we can easily increase the number of host cell proteins that we can identify, whether we do it using a single peptide for identification, or move that up to 3 peptides or even 5 peptides. We find more detail on that. And this is the NIST antibody standard. So that's a protein that's well described, where we know how many host cell proteins are back. So we know that the proteins that we identified are actually truly in there. So to summarize the webinar, the pillar array column or the microPAC column is a unique approach to LC column design. We don't use beads any longer. We don't pack under high pressure a PAC bed with all the possible problems that might occur over time in use of that, but it will achieve the possibility to run a wide range of omics applications in the low flow range. But what you will get is a not seen before reproducibility with an outstanding sensitivity and an enormously improved robustness. Whether you need to dive into the really complex samples, or your challenge is more in the high sample numbers that you need to do. And with that, I would like to to show you that there are plenty of papers available. So if you are interested, let us know. And with that, I would like to thank you for your attention. And if you have any questions, please just let me know. Thank you very much.
Thanks, Robert. Very nice presentation. Congratulations. The data that you showed are very interesting. We have Giuseppe from USP São Paulo, São Paulo University, asking you about the limit of sample. Could you read the question?
Yes, I can. So, Giuseppe, thank you very much for the question. I would try to keep the sample at a 200 centimeter long column around 4 micrograms of protein, of digested protein content, and on the 50 centimeter, probably in the direction of 1 to 2 micrograms max. Although I know that with the later generations of mass spectrometry, you can use a lot less of sample if needed. So if you have between 100 to 500 nanograms of digest available, that is actually really, really good for the modern mass specs.
Okay.
Does that answer your question a little bit?
If Giuseppe has more questions, please.
Yeah, so Giuseppe has another question. So currently we only have C18 separation. So the most used separation mechanism in the proteomics region for the mass spec dimension. Like I said in the beginning, so we are expanding our facilities a little bit. So I hope in the future, I've got my own personal wishes as separation mechanisms, and we'll see what is possible. One of the differences compared to a normal bead is that we have been able to make our pore size a little bit wider. So typically, the C18 column has an 80, 100, 120, maybe 175 angstrom pore size, which is really well if you work with tryptic digests. But there are samples where the amino acids are a little bit hidden away in the protein, and the unfolding of the protein is a little bit more difficult. And then Lyc could be another enzyme that could be used, but we know Lyc creates larger peptide chunks. So our pore sizes over all these million of pillars is ranging from about 100 angstroms to 300 angstroms. So if you've got larger chunks available of peptide, we can actually separate them better out as well. Well, yes, thank you for that remark. So Hela is on my list, obviously, because in the early 2000s, there was actually quite a lot of work on Hela in proteomics, but Hela is also one mechanism that's really good for metabolomics. I've showed you the data on the single cell column. Now that's not the perfect format for it, but a lot of silica chemistry is actually bare silica. So once we have the time, one of the things I'd like to investigate is what happens if we run our non-treated pillars in a bare silica conditions, and can we mimic a helix separation? And then you could do the Ehrlich idea that's been published a lot, also by one of our users that I mentioned, Goran Matulovic, where you combine C18 and Helic together. And that would be really fun, at least for investigation purposes.
Ok. Alguém mais tem alguma questão? I think that we could think to finish. The presentation will be available in the YouTube channel from Analytica. We recorded the presentation. We will send the link to everybody that subscribe and attend the webinar after Monday. Okay? If you have any question, please send it to us email, and to be free to contact directly Robert after the webinar to discuss any particular issues. Okay? Thank you everybody for attending, and I hope to see you again in next webinar. Thank you, Robert.
Thank you very much, Luis, for helping me set this up, and thank you to all the participants for taking the time to listen. Bye-bye.
You are welcome. Okay, bye-bye.